The effect of horizontal airflow over mountains and hills creates a very unique phenomenon. Looking at the diagram, we can see a mountain being exposed to horizontal airflow from the left. As the air flows over the mountain, it starts to oscillate in a wave-like pattern. These oscillations are known as mountain waves, lee waves, or standing waves. However, to create these oscillations, certain conditions must prevail in the atmosphere. Firstly, the air must be very stable. Otherwise, the airflow when reaching the mountain would rise vertically and destroy the oscillation pattern. More importantly, though, it is the layer of air at, around, or just above the mountain ridge that must have absolute stability. Another condition which must be met is that the wind speed at the level of the ridge must be greater than 15 knots and increase with altitude. The direction of the wind in relation to the mountain's orientation is another crucial factor. The winds must flow within 30 degrees either side of the perpendicular. The diagram shows an example of a mountain range aligned north-south. The direction of airflow that's needed to help create the mountain wave must either be from the left, between 240 degrees and 300 degrees, or from the right, between 060 degrees and 120 degrees. When all these conditions are met, the mountain wave will be created. Fortunately for pilots, these oscillations may become visual. Let's take a look at one of the crests downwind of the mountain. Here we can see air rising on one side and descending on the other. This is important. When the air is forced to rise, it will cool adiabatically. And if sufficient moisture is in the atmosphere, condensation may take place and cloud will form. However, when the air is forced to descend on the other side of the crest, it warms adiabatically, and any cloud dissipates. Notice the shape of these clouds. Their lens-like shape has led them to be called stratocumulus lenticularis or altocumulus lenticularis, or for short, just lenticular cloud. Here are typical examples of such clouds. Their shape can appear odd and unusual, leading some observers to mistake them for UFOs. There are other visual clues for the pilot. One of these is the type of cloud that shrouds mountains, making it difficult for the mountains to be seen from the air. These clouds are called cap clouds. A famous example of a cap cloud can be found on Table Mountain in Cape Town, South Africa. These clouds are created by the air cooling adiabatically when forced up onto the top of the mountain. There is one other cloud that is probably the most significant, since it implies the location of the most severe turbulence. If we look at the flow of air underneath the first wave crest, we can observe a circular rotation of air. This zone is the most dangerous, since the wind is changing direction constantly in a very confined area. The clouds that develop here are called rotor clouds or roll clouds. As was mentioned earlier, clouds are the visual clue to what is happening to the airflow and also the possible location of turbulence. But don't assume that without the rotor cloud or lenticular cloud that there is little or no turbulence. There most certainly can be. So, how can we recognise a potential situation for the creation of standing wave activity? Firstly, expect it whenever you cross mountain ridges and hills. especially in windy, stable conditions. Examine your route and identify areas where high ground or mountains exist. Get the forecast charts for wind directions and speed with altitude. Then compare these to the locations on your route where there are mountains or high ground. Since we know the turbulence is downwind of the mountain, and especially within the rotor zone, when flying close downwind of mountains, do not fly below mountain level. In fact, try and avoid the mountain vertically by the highest margin your aircraft and operational parameters will allow. If you have to penetrate the rotor, disengage the autopilot, fly at turbulent penetration speed, and let the aircraft ride the turbulence. Fighting the aircraft and the atmosphere may cause damage to the aircraft structure. Enter and exit the system using the shortest possible route. Never initiate turns. These will give greater G-loads and reduce the aircraft's performance envelope significantly. The most important thing to remember is, never fly downwind, parallel to the mountain, below ridge level. That's where the rotor zones are. There is another situation in the atmosphere that can give rise to turbulence and wind shear. In the lesson on temperature and pressure systems, we said that there may be times when we can experience temperature inversions. If you remember, inversions are where temperature increases with altitude. If the temperature inversions are strong enough, then as a result of the changing density, we can get significant changes in wind direction and speed through the inversion. This leads to wind shear, and as pilots, we need to be made aware of them. If the temperature at 1,000 feet is 10 degrees Celsius higher than at airfield level, then an MTI is issued. MTI stands for Marked Temperature Inversion. If you're told that there is a marked temperature inversion at an airfield, you must expect turbulence or wind shear on the approach or takeoff phase of flight. Strong inversions and MTIs are very common over land, at night, within high pressure zones where the ground can cool rapidly. Turbulence of any kind is something we wish to avoid. It is especially dangerous to aircraft on the approach or landing phase of flight, since the aircraft is at low speed, low altitude, and is experiencing high amounts of drag. Fly with great caution and respond promptly to turbulence, and monitor your airspeed closely. Let's now look at how we actually report turbulence. The table shown here relates to the three levels: light, moderate, and severe. Each intensity is described using both aircraft reactions and occupant reactions. Looking at moderate turbulence, we can see that this will be reported any time that indicated airspeed fluctuates irregularly between 15 to 25 knots, and G changes of 0.5 to 1 G are experienced. Notice, though, that the aircraft remains in positive control at all times. Looking at the reaction of the occupants, we would report moderate turbulence any time passengers feel definite strain against the seatbelts, if objects are dislodged, and food service and walking is difficult. Before we finish, let's briefly examine severe turbulence. Notice that indicated airspeed fluctuations and G changes are far greater than that for moderate turbulence. And more importantly, the aircraft may be momentarily out of control. Because this situation is very serious, immediate diversion is necessary. Finally, examine the table and note down the differences between the various intensities. Remember, any time your aircraft is exposed to moderate or severe turbulence, it is compulsory by law to report the incident. Provide as much detail as possible, including location, intensity, time, and aircraft type. The report can be relayed to the air traffic controller if there is time, or alternatively to the nearest Met office in your area. This helps with future forecasting, but more importantly, informs other pilots of the problem.